gives the lecture in English. I will keep doing so. So today we give a short lecture on cubic spline interpolation. Maybe you already have seen that at some point of your lives. Yes or no? No? Yes? No? Yes. Yeah. So today is, you can see them from here? I don't know. Cubic spline interpolation Okay. So let's define the set of cubic splines. So we define the set of cubic splines, and then we proceed to show that this set is finite dimensional. So we can find a traditional algebraic basis, okay, a Hamel basis, if you know what it means. And since we have a Hamel basis for the set of cubic splines, we can show that this interpolation by cubic splines, it's unique, and we also give two different types of cubic splines, which make a difference when you try to compute, when you try to deal with boundary value problems or initial value problems. So these two types of interpolation by cubic splines can make a difference. So let's define the set of cubic splines. Definition, I guess. Definition. Menor? Yeah, but when I go from the far right, maybe you can see it. I don't know. Okay. Okay. We'll see. So the set of cubic splines. The set of if you don't understand my handwriting, feel free to complain. The set of cubic splines. Let's call this S delta, where delta is a partition of a given interval AB. We'll see this. Is defined as all the functions phi belonging to C2 of the interval AB, okay, such that for each subinterval, such that phi is a cubic polynomial is a cubic polynomial in each subinterval of the interval AB. On each, let's try to do it. On each xj plus 1 subinterval. Subinterval of the bigger interval AB, okay? So this is a C2 function on the whole interval, but at each subinterval it is a cubic polynomial, so it's a C3 function, or a C-infinity function in reality, right? So this is what a cubic spline is, okay? It has this smoothness on the whole interval, and each subinterval is a cubic polynomial. So now, as I said, let's maybe draw a picture. No, not really. Okay, so delta, that delta is a partition. Delta is a partition of A, B, uniform partition, okay? Uniform. So we are dealing with a uniform mesh, all right? For the whole lecture, we'll be dealing with this delta being in a uniform mesh, which is a partition of the bigger interval AB. Okay, so there's that. So now, as I said, we want to show that this set is a vector space, so it's obvious, but it is finite dimensional. So I won't show that it's finite dimensional, but I will show what are the bases of the subspace. Maybe I'll put it as an exercise in the list to show that this has the dimension of n plus 3. Maybe J uniform, let's say xj plus 1 minus xj is always equal some given age, okay? So this is what it means by uniform. And j is varying between 0 until n minus 1. All right? Yeah, so this is good. Okay, basis for S delta. Basis for of S delta. So the elements of S delta are called cubic splines. All right, so this is obvious from the definition. And the elements of the basis, we call them B-splines. All right. So let's define, let's show what are such elements of which we call B-splines, right? So we take, I will continue maybe here, okay. Basis of S delta. We take small s, j, it's a function of x, to be, now this is a little tricky, okay, so this is 0, where when x is greater than xj plus 2, it is, yeah, it is 1 over 6h cubed xj plus 2 minus x to the power 3 when x is between xj plus 1 and xj plus 2, xj plus 1, xj plus 2. And we can keep going. Yeah, I guess since my time is short, I'll give them. Okay. So we have this. And we can keep doing this trick until we get 2 over h xj plus 1 minus x plus 1 over square. So this is a big formula. It's all written in the book, but I guess since we want to show that this is a basis and these are important bases of the cubic spline set, maybe you have to look at them at some point, the explicit formula. Xj plus 1 minus x to the cube when x is between xj and xj plus 1. Okay. So we have 0, this expression, this bigger expression, and we have still more expression. Okay. And 2 over 3 minus 1 over h squared x minus xj squared, yeah, minus 1 over 2 h cube, yeah, cube, x minus xj cube, when, then again, xj minus 1, xj, when x is between xj minus 1 and xj. We still have one more. Cube, 6h cube, x minus, now xj minus 2 to the power 3. When when xj minus 2, okay. Xj minus 2 and xj minus 1, right? So we keep doing, moving to the left. And finally we have 0 when x is less than xj, j minus 2. So I hope this is clear, right? It's a big definition. So let's make a comment. So this is called the B-spline, okay, basis of x delta, B-splines. So this is called the B-spline centered at xj, okay? So this is the B-spline centered at xj. So little sj is called a B-spline it's called a B-spline centered at xj, with respect, so with respect to the uniform partition delta. Where is delta? Right there, right? Delta partition of AB, uniform, with respect to delta. Okay? Okay, so are we good until now? It's a big formula, so it's not that hard to show that these functions are C2 on the whole interval. We have to show the continuity at each of the xj minus 1, xj minus 2, xj plus 1, xj plus 2. And it's clear that this belongs to S delta. And we want to show that this is a basis. This Sj for j varying between 0 and n minus 1 form a basis of the C-spline vector space. So just to abstract a little bit, xj is just a function which depends on parameters. It depends on the mesh point which you are centering your B-spline, right? In this case, xj, okay? So it depends on the xj. It depends on 2 j's to the left and 2 j's to the right, okay? Okay, so let's have that in mind. And now we want to show that this is a basis, but we can't show that this is a basis actually, because it's not. For this to be a basis, we have to increase this set of SJs with 2 extra B-splines at the boundary of our interval, at the point n, xn, right, and x0. So then we have a space big enough for it to be a basis of the S delta. So we have to increase this size of the set. So let's just draw a picture maybe of SJs. We have the middle xj. We have 2 to the right, xj plus 1, xj plus 2. And here xj minus 1, xj minus 2. And the picture should be something very smooth on right here, which decays to the neighboring points really fast. Okay, so something like this. It reaches its peak on the centering xj, and then from the neighbors it has a fast decay. All right. Now for so B-splines at the boundary. B-splines at the boundary. At boundary. Introduce 2 extra points. Introduce 2 extra points, x minus 1 and x n plus 1. And then we consider the B-splines centered at each of these points, okay? So we have 2 extra B-splines associated with the interval AB, the ones we had before, the Sj, S sub j, And now we introduce two extra ghost points at far left from the boundary, far right from the boundary, and consider the B-splines at each of them. Introduce two extra points and consider their B-splines. And consider their B-splines. Okay. Now we can state this as a theorem, I guess. Okay, so theorem. The set. Okay. The set small sj from j 0 to n union those two B-splines, right? Let's call them, consider their B-splines. Let's call them phi minus 1 and phi n plus 1. Phi minus 1, phi n plus 1. So this set form a basis of the C-splines of the cubic splines set. This set is a basis basis of S delta. S delta. Right. It should be a capital N, yes. What's the problem? J is very, no, okay, yeah, because it's J, right? Yeah. Because xj, when j is n minus 1, we have xn, correct? xn. So we should consider here xn plus 1 and the B-spline centered at xn plus 1, which is phi n plus 1. Okay? So the first theorem, this is a basis. Okay? Those type of functions together with those two B-splines, which are not really, which do not really belong to the initial partition, but we have to introduce them in order for this space to be big enough for it to form a basis. Okay. Okay. So I'll give a scratch of the proof. Okay, so I have to erase this. Do you guys know if this room will be available after the traditional time, or if we have any classes in this auditorium or not? Are you guys okay with staying a little bit longer than the traditional time? Maybe 20 minutes, maybe? Okay. Okay, so let's give a scratch of the proof that forms a basis of S delta. Okay. Proof. So we have to check that set is linearly independent, right? And that it spans the whole S delta, right? So linear independence. Linear independence. Okay, so how do we check linear independence? What we have to show? Right here. Let next Cj together with phi j. Yeah. Minus 1. Now I have to sum to n plus 1. Yep. Equals 0. So what do we have to show here? Do you remember from linear algebra? We have to show that all the Cj's are 0, right? Then the B-splines are linear independent, okay? For all J. Okay, so let's do it. Let's put a point. Xi I from 0 to n. Yeah. And also we compute the derivative of the B-splines. Phi j at xk. Minus 1 and plus 1 equals 0 and k 0 until n. Okay. So we can rewrite that equation as a matrix times a vector. And we want to show that the coefficient matrix is non-singular, right? So we can rewrite that as we set the vector C to be the vector, the column vector C0, C1, and so on until Cn. All right. And then that equation, say, let's put it like this, star 0, then star becomes A times C equals 0, where A for A the matrix A, right? Something like this: 4, 2, 0, 0 to the end, 1, 4, 1, 0 to the end, and then we shift 1, 4, 1, 0 to the end, And this keeps going, okay? It keeps going until the last point, which is 4, 2, 0. Above I have 1, 4, 1. Okay. And this should be this. Okay. We have a 0 here. Maybe something like this. Yeah. Okay. So the point is that A, it's diagonally dominant. You remember from linear algebra what that means? Hence, A is diagonally dominant. Diagonally dominant. Just so you guys can remember what that means. It means that absolute value of A I dominates the sum of the absolute values of A I J over the whole line. So this is what it means. So for a matrix to be diagonally dominant, is this okay? Okay. So what we know about these types of matrix? Yeah, it's non-singular. It's the same. Yeah. Okay. So therefore, diagonally dominant. I have to write it here. Yeah. Therefore, that the determinant of A is not 0, right? Non-singular. So, therefore, that A is non-singular. So, what does this imply for the vector C? It's 0, right? Therefore, that which implies C identically 0, because the null space is trivial, correct? So C is 0. So this shows the linear independence of the supposed to be basis vector, right? And now we should show that those vectors span the whole cubic spline set. Okay. Yeah, so the set spans S delta the book does this by explicit construction. So we will not be doing this here. We'll be doing this as an exercise. Okay. Spans S delta exercise. exercise. So now we indeed have that this is a basis. Okay, so it is a base. Okay. 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 Spans delta. Okay, so now I want to show two types of cubic splines that we can use. Okay. Two types of cubic splines. The first type is the clamped. Clamped splines? Is that what it is? Clamped boundary, right? Clamped boundary. Clamped boundary. Interpolation or interpolant. So what does it mean? Let's call this phi C, phi clamped, okay? So this we interpolate by doing such restrictions. Phi C at x, y is equal to our function, right? That we want to interpolate f for a given mesh, a given partition, uniform. And we also restrict ourselves to the derivatives at the boundary. xn equals to the derivative of f at the boundary and the derivative at the other boundary, x0, should be also equal to the derivative of f at x0. Okay. For all I in the partition, that's in the partition delta. Okay, so this is one type of cubic spline interpolation. The other type is what we call the natural interpolant. The natural interpolant, two types of cubic splines, clamped spline. Okay, and the second type we interpolate by doing the following. We still have to match the values. Oh, now it's okay. Clamp the boundary interpolant, natural spline interpolant. which we call phi sub n. This n means natural. And what we do, okay, so here we have these three conditions, right? Those. And now we want to match our interpolating function phi n at each mesh point to our given function f, right? At other mesh points. Of course, this is an interpolation scheme. But now we don't care about the derivatives. We just impose that phi n, the second derivative, at both boundaries to be 0. Yep. So the first boundary equals to the second boundary, xn. So this n is not this n, so this may be not so good. Let's call small n. Small n, small n, and this is small n. 0 equal 0, okay? Okay, so just to see what we have done. The first type of interpolation by cubic splines, we force the function to match our given function at each mesh point. Of course, this is an interpolation. And moreover, we also force the derivative of our interpolating cubic spline to match the derivative of our given function at each boundary. So this is one type of interpolation scheme that you can do using cubic splines. And the other type is basically saying, of course, we match our interpolating function to our given function at each mesh point, okay? J is a mesh point, right? But we do not match the derivatives at the boundary. We just prescribe them to be 0, exactly 0 at each one of the boundaries, okay? This can make a difference when you are studying boundary value problems, okay? So you in some types of PDEs or ODEs, you have to choose one, or you have to choose another, because if you impose that the second derivative is 0 at each one of the boundary, it means that the interpolating function has a stronger decay than this type of function. So this can play a role when you are trying to solve numerically, integrate numerically some types of ODEs or PDEs even. Yeah. So we have the clamped interpolation and the natural spline interpolation, both of them. And now we want to show that these interpolations are unique, which should be, right? You shouldn't have more than one interpolating function for a given f, right? I mean, for a linear interpolation, this is obvious, right? You want to find a linear interpolation between each mesh points. You only have one line. But now you want to find a unique interpolation which at each interval you have a cubic polynomial. So this is a priori not so obvious as the linear interpolation case, okay, you see? But we still have uniqueness here. So this is actually a neat thing to have. Yeah, so I'll just state this with no proof again. I will refer to the book. But let's state what I said. The uniqueness statement of the interpolants. So how can we state this? Yep. Okay, theorem for each f, for every f C1 of the interval AB, we have a unique, let's say there exists a unique clamped boundary, unique natural spline interpolation. Unique clamped boundary, unique clamped boundary, interpolant, for F, right? Our capital F. And also there exists unique natural spline spline interpolant for F. Okay, so is it clear? Mm-hmm. Mm-hmm. Okay. And all this is for remark. Delta is a uniform mesh. Is a uniform mesh. Similar results for delta not being a uniform mesh we can still have, but we don't really care right now. Okay, uniqueness. Yeah, so we have still uniqueness of the cubic spline interpolation. Okay, now, okay, so we have a C1 function. We can find a cubic spline interpolation. It is unique, all right? What do we want to know now? About the error you make, right, when you interpolate something, right? By the cubic spline. So now I want to give an estimate on the error of cubic spline interpolation. Okay, so this is over. So let's give an error estimate for the cubic spline interpolation. Okay. Error estimate. Error estimate. So again, a delta uniform mesh. uniform mesh. Our given function is C4 of the interval. Then we have that the difference in the supremo norm of F and phi C. Remember that phi C is the clamped interpolation, okay? The supremo norm is given by five over 384 times h to the power 4 and times the supremo norm of the fourth derivative of f. Okay. Okay. This h is the size of the mesh, right? So h is x j minus 1 plus 1 minus x j. Okay. So indeed, we can see that the error decreases at the fourth power with the mesh size, right? Mesh size or resolution, right? So this is a good sign, right? That we have something decreasing with the fourth power of the size of our mesh, okay? So this is pretty good, I guess. Okay, no proof again. No proof. Yeah, I guess we have time. So one last thing I want to present today. So you remember that the set of cubic splines that S delta, right, was defined to be the set of all the C2 functions of the interval, which at each subinterval it is a cubic polynomial, right? So you may ask, what do we gain by interpolating? By taking a C2 function on the whole interval and asking it for it to be a cubic polynomial in all subintervals. Shouldn't we take just a C2 function on the whole interval? Why is this important even? Why the cubic polynomial specification? I mean, okay? So I want to show some minimization property of these cubic splines interpolants. Minimization property. Minimization. Take some function u belonging to our S delta. No, S delta no. C2 of the interval AB. So u is just C2, but not a cubic spline. Okay? Which interpolates interpolates F as u of xj equals f of xj, u of derivative of u at x0 equals derivative of f x0, derivative of u at x n, capital N, matches the derivative of f at capital X capital N. Okay. And u interpolates f like this, okay? Then the L2 norm of the clamped spline interpolation is always less than any L2 norm of u, okay? So let me say it again. You take any C2 function which interpolates f like a clamped spline, right? This tells you that the cubic spline, which interpolates f like this, has the minimum of all L2 norms of any C2 function which also may interpolate f like a clamped spline. Clamped spline. Is this clear? Or the L2 norm is just the integral, actually, L2 norm of second derivative. Yeah, okay. Okay, so this is just the second, okay, let me. This means integral phi c dx less the integral of u second derivative x dx ab. So in some sense, the cubic spline interpolation is the minimal. It minimizes. It's the minimal element. How can I say this? Okay. So the cubic spline interpolant is the minimal element of S delta. Remember S delta, the cubic splines, which interpolates F. Any other C2 function which may interpolate F is always greater in the L2 norm, is always bigger than phi C in the L2 norm sense. Okay? So this is a nice minimization property which tells you that the effect of choosing cubic polynomials between each subinterval indeed has a difference. You see this from that? Because U is just a C2. At each subinterval of the mesh, it is not a cubic polynomial. So the effect of adding cubic polynomials between each subinterval of our mesh has the effect of minimizing, in some sense, the function, of minimizing the L2 norm, and then again, this has implications of the error. Where was the error? The error is here. So you may guess that if you interpolate our f with some other function, which is also C2, but not a cubic spline, this error would be bigger, okay? So that is somehow a heuristic argument to show that indeed the cubic splines between all the C2 functions are the elements which minimize the error. Okay, so this is clear. Okay, so I guess I went fast and I managed to finish on time. Yeah. Okay, any questions? It was a very fast lecture, very